Hey everyone, today we're going to be talking about network policy APIs in Kubernetes. We're going to take this in two phases where we first explore what a network policy is as an object and how it impacts your namespaces inside of Kubernetes. Once we get beyond that, we're going to take a look at the other APIs. Now, these APIs aren't necessarily part of core Kubernetes, but they're CNI specific APIs that you can use to express the type of networking rules that you might want. And these can be delivered by CNI plugins like Cilium or Calico, and there may be some others out there as well. So starting off with network policies as a whole. Those of you familiar with Kubernetes probably already know that Kubernetes supports a network policy object. And this is something that we're going to apply early on in this video. Now, the network policy object allows you to express egress and ingress rules. And this is not too dissimilar from the types of egress and ingress rules you might set up on a conventional infrastructure or cloud provider like an AWS with your security groups. Now, the big difference between Kubernetes network policy and doing this outside of Kubernetes is oftentimes the CNI plugin that you're using to facilitate your network traffic is the one enforcing the policy. So unlike AWS security groups and unlike some more conventional, switches and routers and things like that, this CNI plugin lives in the cluster and understands the virtual IP addresses of the pods, perhaps the services, and so on, at least the pods. So it's going to provide us with a way to, at a very low level, or I guess at more of a very Kubernetes specific level, express how traffic rules should go. So think about a more conventional security group you might set up in a place like Amazon. Oftentimes you'd say, this IP address can only go to this other security group or other IP addresses based on this port or port range. But in Kubernetes, we know that IP addresses generally are a lot more ephemeral. Our pods are getting restarted and recycled. So we want our network policy to be able to act on things like labels that could potentially qualify multiple pods and have rules based on different labeling, but then also still have the functionality to do things like CIDRs. So this is something that we're going to take a look at in a moment, but probably one of the core things to start off with is knowing that any Kubernetes cluster should be able to accept network policy objects. However, you do need to be running a CNI plugin that is capable of respecting and enforcing those network policy objects. What I'm getting at here is if you were to run maybe a more basic Flannel deployment, let's say. So Flannel is a really easy to deploy CNI plugin that will facilitate your pod networking. You can start adding these network policy objects, but you're not necessarily going to start enforcing traffic. Those policy objects will just sit in Kubernetes unenforced. But if you're using a provider or a plugin that supports it, and this could be things like the Cilium project, Calico, and Weave, these are a subset of CNI plugins that are capable of enforcing those policy rules that you set for your cluster in your namespace. So with one of these in place, we can start taking a look at this network policy object. All right, so the first thing we'll take a look at are what pods are running on the system here. So let's set up a watch with kubectl, and we will do this for the get pods command, and let's do it for all namespaces. So this is what we have running on our system today. Pretty standard Kubernetes deployment, although it's not running highly available. And as you can see at the top, I'm using Calico as my CNI plugin. So the things that we are going to be adding to Kubernetes from a policy standpoint are going to be reflected in Calico, or in other words, enforced by Calico itself. So let's dive into some of these first policy constraints. Now, with Calico using the pod-to-pod networking, today, there isn't going to be any restrictions in pods communicating with other pods. So as an example of this, if we have two namespaces, org2 and org1, two organizations, and then we've got team A that lives in org2, or org1, sorry, and then we have team B that lives in org2. So two pods, two different namespaces, they will be able to intercommunicate without any issue. Let's take a look at what exactly this means. So if we go into the team A deployment here, and I'm going to set up that watch one more time down here. We will bring it down a little bit. Good, good. All right, so we have got team A. It is going to live in the org1 namespace, and it's going to run on a container called nginx curl, which is just an nginx image that I put some extra tools inside of. So let's go ahead and apply team A. So kubectl apply team A.yaml. And now in the bottom here, in a moment, we're going to see team A show up. It is in the org1 namespace, and it is now running. And then team B is not too dissimilar. So if we look at the team B YAML, it is the exact same image, but it is obviously running in the org2 namespace. So let's go ahead and deploy this one as well. So we will apply team B.org. Oh, sorry, wrong one there. Let me delete that one real quick. We will come back to that manifest. Okay. Give that a second to terminate, and then we're going to apply the team B YAML. Got a little ahead of myself there. All right, so we've got the team A in org1, and then we've got team B in org2. And like we've talked about, communication should just be open by default in most Kubernetes clusters. So let's test this out real quick. If I exit out of here, clear it up, and let's start off by execing. So we're going to run an exec command interactively with TTY. Namespace is going to be org1, and we're going to go into the team A pod and open up a bin bash or start a bin bash process. So now we're in team A. Let's do some testing with team A. Can team A access the external internet? Yes, team A can access the external internet. Can team A access team B's pod in the org2 namespace? So we can access this via the DNS record, which will be teamb.org2. And this, although this is an nginx, basic page, that's exactly what we expect. So team A can communicate with team B, no problem at all. Let's back up a little bit and do the same thing for our team B. So again, team B is in the org2 namespace. We'll flip this over to team B. Let's go ahead and curl team A.org1 to see if it goes out. No problem, pod-to-pod communication works. And then just to sanity check here, we'll do a curl for google.com, and the external internet seems to be working just fine as well. So overall, team A, team B, communication is completely open. Now we're going to start taking a look at network policy itself. Now, my goal in this first example is to ensure that any traffic coming into team A is accepted on port 80. Any other traffic will not be allowed from an ingress standpoint. Team A will also be restricted in what it can egress. We are only going to allow team A to communicate to the team B pod in the org2 namespace, as you can see in this graphic. So let's take a look at what a manifest might look like. So I'll exit out of here. We'll go into the org policy YAML. So this is a network policy object. And as you can tell, based on some of the initial pieces of it, it has its own API version. Network policy has its name and a namespace that it applies to. So these are namespace scoped objects. It's going to go into org1. Now, probably one of the most important and sometimes the most confusing pieces is at the initial level of the spec, there is a pod selector. That means all the rules I define in here are going to apply to the pod that is satisfying, or pods that are satisfying the pod selector here. Now, it's going to become more important later, but for all intents and purposes, assume curly brace open, curly brace close represents that it should match all pods. Now, since this is a namespace scoped object, that means that this rule I'm setting up will apply to any pod running in the org1 namespace. And you can also specify policy types. So you could split these out into different files or perhaps only define one. But I'm going to be expressing both ingress traffic coming into the pod and egress east-west traffic from the pod in this manifest. So first rule, pretty simple. Inside a spec, we have an ingress line. We can add a from array, so we can effectively have a multitude of these, right, inside of here. But for now, the only thing we want to specify is that we allow TCP traffic on port 80 to any pod in this namespace. Pretty simple. And then additionally, we've got the egress rule here as well, pretty similar on the same level as ingress. And egress is going to say two things. The first is what we just talked about. We want to ensure that team A can send traffic to team B in the org2 namespace. But we also want to make sure that team A can resolve DNS, because that's how granular this gets. And by doing that, we can achieve it with a rule for all traffic being allowed over port 53 through UDP. Now you'll notice that these rules can match based on label selectors. This is a very Kubernetes-like approach. So in order to be able to send traffic to the Team B pod, we need to ensure, if we look at the Team B pod for a second, I'm going to that other one that I'll be showing you later. Go to this Team B pod. The Team B pod needs to have the appropriate label in order to match the label itself, right? So that needs to be able to be on there to resolve and work okay. And additionally, with these labels, we can see that the namespace is also labeled with names so that it will resolve appropriately to this namespace selector. So very label-heavy mechanism. Now, when we apply this, and I'm going to go ahead and set up a watch one more time in the bottom here. So let's do that watch, but this time let's do it for network policy in all namespaces. That way you can also see that there's no other policies running. Okay, so with this network policy, if we go ahead and apply the file here, which is the team netpol, now it exists in the cluster. Now, it's really important to note, and this is what trips a lot of people up with network policy in my experience, that by default, all traffic was allowed, right? And now we've put a bunch of allow rules with a policy, which might kind of trip you up. It's like, okay, all traffic is allowed, but Josh didn't go in and deny any traffic. He just put allow rules in. So isn't the effect going to be that everything is allowed? So how network policy is going to work is that when a network policy object is present, whatever gets satisfied in the pod selector, for anything that doesn't have an explicit allow rule, it is now going to be implicitly denied. So it's like this binary switch of on-off. So basically, the impact we should see when we test is that by allowing port 80, we haven't just allowed all traffic and then explicitly allowed port 80. By adding this into the namespace org1, we've basically said, all right, I'm going to allow port 80. Every other port is implicitly denied going forward. So that change in functionality can be really tricky conceptually. All right, so now that we've kind of got that in place, let's see if we can test this out. So, and actually, let's leave this open because it might be helpful to reference it throughout. So let's start off by execing into Team B, actually. We'll start with that. So Team B's org2 namespace doesn't have any network policy in it, which means if we were to go to google.com, assuming it's spelled correctly, it should resolve without an issue. And it's going to send traffic over to Team A over port 80. So if we curl Team A, and this is org1, we still can access it through Nginx over port 80. So since Team A is allowing that, it seems to work just fine. So that's pretty good on the Team A front, or Team B front. So if we get rid of that, and then we instead go to org1 Team A, what implication does this new object have on Team A? So let's test it out. If I curl out to Team B and go to org2, it still works. And that's exactly what we'd expect, because back in our policy, we can see here that we're allowing traffic to the org2 namespace for apps with the Team B label. Very good. Now, what happens if we curl google.com? So if we send that out, now we're frozen. So we know that Team A used to be able to access google.com, but due to the fact that a network policy lives in this namespace and that this pod satisfies the pod selector, which is all so far, it doesn't have an egress rule to let itself go out to the external internet or google.com. Now, interestingly, it does have an egress rule to allow all traffic for UDP, so you probably know where this is going. If we do an NS lookup on google.com, we can resolve the google.com IP address. We're just unable to actually go out to that external IP address with a request because egress is going to prevent us from doing that. So this switch from a full allow all to an implicit deny with only explicit allows is a big change in our namespace. Another way to show the implications of this network policy would be to move team B into the org1 namespace. So let's set up a watch one more time here on we'll do watch kubectl on get pods for all namespaces. Okay, so we'll set up a watch here. And then let's go ahead and delete the team B org2 deployment. So I will go back to where I've got this repo. So oops, there's an S there, netpol, and then manifests. All right. And let's go ahead and delete the team B YAML file. All right. So that should terminate team B out of here. And then let's set up a YAML that deploys team B into org1. And that's that other YAML you kind of saw a preview of earlier. So if we go to team B org1, this is the exact same manifest. The biggest difference being that we are going to be deploying in the the org1 namespace. So let's try that right now. So I'll do an apply for team B org1. All right, and it's creating, and here we go. So now we've got team B living in org1. So now they're both in the same namespace. Now, if you think about this, based on what you know about network policy so far, what exactly should this change? So let's check it out. If we go back and exec into team B again, because we already have tested out team A and nothing's really changed with team A, org1 now, sorry. Okay, so team B, can it curl to team A is the first thing to check out. So we know it used to be able to, and now we can just use team A since it's in the same namespace. And it hangs. So clearly team B is now impacted by that implicit deny. And again, this is where adding network policy and the behavioral change of networking can really start to throw you off. You have to think, well, team B qualifies for that policy and it's being impacted by it. It still is able to do things like an NS lookup on team A and figure out where it's at in the cluster, but it can't ping it from, or can't curl to it. It also can't curl to google.com anymore because it's being impacted by that policy. Now, interestingly, and this throws me off sometimes too, if we exec into team A again, team A is still able to curl to team B. And this is because while there was a namespace selector, there was also that pod label selector. And since it satisfies the pod label selector of still having app team B, it will let that traffic through. So team A can communicate with team B, but team B can no longer communicate with team A, nor can it get to external traffic. Now, there's obviously a couple ways that we can approach this here. So let's go ahead and bring this up to the top, and we'll keep our watch down here. And what we can do is if we actually, let's get rid of this watch. We don't need it right now. Let's go to the org pol one more time. And if we wanted to say, change this behavior, say we want to ensure that all the rules we had specified work for team A, but they don't impact team B anymore. And this could be something you want to do or not. Sometimes you want namespace level policy. Sometimes you want pod specific policy. So, one thing that we could do to approach this is we could make another network policy object, add it to the namespace, and add some new allow rules for team B. That would be super adequate because these are kind of additive allow rules in the namespace. Or we could come into this original netpol and we could update the pod selector. So if we change the pod selector to basically be the same as what we've got down here, so we'll do pod selector match labels, and then we will do the label name, or actually, sorry, this is the label key, which is app, and we do team A. Now the network policy should only apply to the team A pod. So we'll do a kubectl apply, and we'll put in team A.yaml. Oh, sorry. We need to do the org policy. So this is this file you're looking at right here. We'll apply that, and now it says that it's configured. So as you could probably guess here, our change should be that if we exec into, let's clear this out, if we were to exec into team B, still in the same namespace, okay, if we exec into team B, we can now curl google.com. In fact, we can also still curl team A, because team A, while it does have network policy applied to it, is once again allowing traffic on port 80. So what's great about this kind of process is you can start adding different network policies into a namespace. Another example I can show you is that many times people will set up kind of like a default deny all, if you will. So say you have a multi-tenant Kubernetes cluster and you want to ensure that by default, in this example, all ingress traffic is completely blocked. You could make it ingress and egress if you just updated this to also say egress, right? But in this case, we'll just say it's ingress. So setting this up and having it add to a namespace means as users start deploying their pods will be able to egress no problem, but they won't accept any ingress traffic. And then just like a security group in Amazon, a team could go in and add their pod, and they could make another network policy for the same namespace that starts to poke holes in this default deny all. Because remember, these are allow rules. Once they're present, everything not qualified or explicitly set is denied, right? And then as we add more and more policies, it becomes this kind of additive list of allows based on how all the pod selectors and so on resolve. So you can start to kind of see how network policy by default will work in Kubernetes. Now let's talk a little bit about the limitations you might run into when using these network policies. Now, first thing I'm going to do is just a little bit of cleanup here. So let's get back into that folder for manifests. And I'm going to bring Team B back into its own namespace because this example is going to require pods in their own namespace. So I will do a delete of the Team B org1 YAML. And then we're going to bring Team B back in, but it's going to be in the org2 namespace to represent some of these examples. So we'll do an apply. We'll do -F, and this will be the Team B YAML. All right, so in a moment here, we should be back to a place where we've got Team A and Team B in two different namespaces. Perfect. Now, you can start to see how network policy is pretty powerful and allows you to do some really cool security group-like or firewall-like rules in your cluster. But there are some limitations, and while this is just a few of them, it's important to kind of call these out and start to get your brain thinking about the limitations in case you hit them. So one of the limitations is obviously that you don't have the ability to inverse the structure. And what I mean by that is you can't specify explicit deny rules, right? You're kind of limited to this notion of you allow things and then you implicitly deny everything else. But perhaps you want to take an opposite approach where you want to allow a bunch of things, right? And just explicitly call out the denial of other things. You don't really have a clean way to express that. It's done more implicitly. You also don't have the ability to do more advanced expressions on the selectors. So things like and, or, contains, different things for how you specify the evaluation of pod selectors for labels and so on. You'll also notice that there weren't any, or didn't appear to be any ability to do layer 7 rules. So if we want to get more advanced with things like doing specific methods or paths and block just those based on the request, we may want to be able to do that with a really kind of granular layer 7 type policy. And then another one that's probably the biggest one for me is network policy, as you've seen, is namespace scoped exclusively. So what this means is by default, like say you want to do like a blanket denial for your cluster, just like we saw, you would actually need to have, let's see if I can find the file here. So this is the deny all ingress. You need to have policies like this in all your namespaces. So every time a namespace gets instantiated, you need to create one of these, create one of these, create one of these, which could work okay. But perhaps you want to have kind of like cluster-wide rules that the administration team sets up, and then people use the namespace scoped constructs to start poking holes in it. You don't want to kind of maintain the global state or the cluster-wide rules in every single namespace replicated. So this is an example of where some of the CNI plugins have come up with their own definitions for network policy. And just like we've seen for some things like ingress, rather than baking all those into annotations, most of these companies or projects have set up custom resource definitions, or CRDs, to give their own custom API. And the two most common ones that I've seen and that we'll look at are the Cilium network policy and the Calico network policies, which are called both network policy and global network policy. Now, you can dive into the documentation on these different projects, and I'll put their documentation in the description of this video. but it's going to be pretty clear that they are reasonably more capable. Now, admittedly, if you don't need their extra capabilities, it's probably smart to stick with the network policy, because why not have something that's portable across CNI plugins? But if you do want some more functionality, it may be beneficial. And I'm going to show you a global network policy now, and this is Calico's CRD, that provides cluster-wide networking rules to be applied. And it's actually a model that I like a lot. Now, since network policies work explicitly, well, mostly off of labels, one of the things that I need to make sure is that my cube system namespace, if I look inside of here, get namespace cube system, let's do YAML. I need to make sure this has a label on it that I can evaluate against. So I'm just going to replicate its name and put a label in metadata called cube system. And to do this, we can write a command like this, kubectl label namespaces cube system, and we're going to add in the label name equal to cube system. So I'll go ahead and label that now. And if we do the get one more time here, so there it is, you can now see that we have the label cube system. So when I set up a global network policy, I can rely on my namespaces being labeled. I've already labeled org1 and org2 in their respective manifests. All right, so let's take a look at what a global network policy might look like. And before we do, let's make sure we don't have any network policies hanging out, because I want to make sure we have a totally clean slate to understand how this works. So we're going to go ahead and delete this existing network policy. All right, now it's gone. So we have no network policies in any of the systems. And we're going to take a look at the global one. So let's get into that right now. Now, you can ignore some of the comments here. They just kind of make it look ugly. But basically, we have this object called the global network policy, which is a CRD with Calico. Now, the global network policy is going to allow us to specify some extra features we couldn't with the normal network policy. As an example, we have the ability to set an order in here. Now, order is something that is going to allow you to specify the order in which the policies are evaluated. So in Kubernetes, we know that we just add a bunch of policies in, they're all additive, they're allow all, or sorry, they're not allow all, but they allow things explicitly and then everything else is denied. But with Calico, and at least with global network policy and Calico's network policy, you can go in and get fancier where you specify deny rules, allow rules, so on and so forth. And you can call out the order in this case. Now, I'm putting an order of 2000 because that keeps Calico's order high enough that the Kubernetes network policy, which I believe evaluates, and it's either an order of 1000 or 100, you might have to check the docs, but basically the Kubernetes network policy is going to be rendered by Calico, if anybody adds that in, and rendered at a lower order. And that will mean that the Kubernetes network policy will take precedence over the global network policy. There are some things that are exactly the same, like I can express ingress and egress rules, and even the ingress and egress rules don't really look too different. You'll notice that I can do these more advanced expressions, not that this one is extremely advanced, but if you go into the Calico documentation, you'll see things like has and more advanced expressions that you can put in here. And I have an ingress rule as well. Doesn't look too crazy, pretty simple based on what Kubernetes already provided me. But obviously the biggest gain that I'm getting here is I'm applying this as a cluster-wide policy. It should impact everything in the cluster altogether. So let's apply this and see exactly what it impacts. So we'll come down here and we'll do another watch. But this time let's do a watch for getting global network policy. And then obviously I don't need to attach a namespace to this get because global network policy is in fact cluster wide. So we will take this, and the key thing with Calico too, that's a little bit different than like how Cilium approaches this, is they recommend you use their command line utility to actually go out and set this up. So to get their command line utility, which will do some extra validation and so on, we just have to go to their GitHub page and grab that Calico CTL command. So we'll go through this really quickly here, and I'm going to bring an internet window over to this screen and see if we can get this working pretty easily. So there we go. All right, so I'm on the GitHub page for Calico CTL. There's Calico 3.5.4 right here, and this is the thing that is going to let me write the Calico manifest into the Kube API server. So let's go ahead and grab the Linux AMD 64. All right, so I will just make a temp directory real quick here. We will get that Calico binary. All right, and once calicoctl is set up, I'm just gonna make sure it's executable first off, and then I'm gonna move it over into my path, and we should just be able to start using it to apply these different manifests. All right, so now that it's downloaded, let's go ahead and check out its rights. It is not executable. Let's go ahead and make it that way. So Calico, and that's it. We'll also make it a simpler name. We'll call it Calico CTL. All right, and then let's go ahead and just move this to user local bin. All right, so now we've got Calico CTL in our path looking pretty good. We can close this page out now and come back. So if we go back to where we were a moment ago, let's go back here. We'll cd again into this repo. There we go. All right, manifests. All right, so again, we've got this global network policy, which is a Calico CRD right here. Good deal. And now inside of here, now that we've got Calico set up, we should be able to go in and actually specify that we want to apply this particular piece. So let's go ahead and do that now. So what we'll do is we will set up some arguments that Calico CTL requires. And this time I'm going to put in the data store, which is Calico CTL Kubernetes. And if you dive into Calico, there's two ways you can deploy it. You could either use etcd as its backing store or Kubernetes as its backing store. And you'll have to check their docs to get an idea of exactly what the differences are between the two. And then I also need to tell it where my kube config is, because it's going to use that kube config to talk to Kubernetes. So in my case, I'm keeping my kube config in kube config. All right, and now we can use Calico CTL. And just like kubectl, it doesn't look too different. We can do an apply command here, and this apply command can be for that file. So we'll do d-k8s network policy manifest global network policy, apply that. All right. And then if we do our watch one more time for global network policies, we should see that now there is a global default deny all in place. So we've applied the Calico policy. Now, this policy, kind of taking a little bit of a closer look at it, you'll notice that it allows all egress traffic and allows all ingress traffic for Kube's system. So if we look at our graphic over here, things like core DNS, the Kube system components, they should have no restrictions in this global policy. They can still intercommunicate. And perhaps if I had a couple other system namespaces that I used for specific system components, I'd want to also include them in this list of allow all. And everything inside of this is able to do any destination traffic to port 53, which is once again just opening up DNS cluster-wide in this cluster. But there's nothing else. So everything else in every single namespace, regardless of whether a network policy exists, should be completely denied. I shouldn't be able to intercommunicate, which basically means if we go back to our pods for a moment here, so let's do another watch here and let's get pods. In our pods, Team A and Team B should pretty much be locked down at this point just because of this global network policy. So let's go ahead and just validate that. We'll run an exec, and first let's start off by going into Team A. All right, so if we try to curl google.com, we seem to be completely locked out. If we try to curl Team B org2, we seem to be completely locked out. And if we do an NS lookup for Team B org2, we are able to resolve that because UDP traffic is allowed throughout our entire cluster. Now, with this model of deny all, you kind of have two approaches you could probably take from here. You obviously, well, really three. One is you could start making even more global policies that allow some traffic, but you probably want your teams to have a little bit more ability to start adding in their own policies. So we can kind of take this one of two ways. Calico, just like having a global network policy, also has a standard network policy as well. So in a hypothetical world, let's say that you want to just do a network policy instead that applies on a namespace level, right? So you would need basically a namespace field here as well, right? And then you could go in and use these more advanced like selectors, and in like Cilium and Calico, they support kind of more layer 7 constructs too, if you wish. So you could do more advanced rules. However, with Calico in particular, I actually prefer to keep my namespace specific policies to be Kubernetes policies. And that's, again, from a portability standpoint, those should be able to translate between different providers for CNI. So unless I have like a really striking need to do more advanced things with network policy, I tend to hold on to the Kubernetes ones and just use those in tandem with the global network policy that Calico offers us. So what exactly would this look like then? So we've got this global kind of deny all policy that exists in one place, can be managed in one place. What if we wanted Team A to be able to egress traffic out to destinations, right? So let's take a look at what that might look like. So if we go into the manifest called allow all egress, let's say hypothetically, I'm Team A, I'm part of Team A, and I don't want my pod to be restricted by any egress traffic whatsoever. It should be able to go to Google, it should be able to go to Team B, no questions at all. So we've got the pod selector and it's set up for Team A. So this policy only impacts Team A. And I'm going to put a policy type egress. And another cool syntax that's important is this expression with the brackets or curly braces allows me to allow all ingress traffic. All egress traffic. So I now am basically saying, Team A, you're allowed to send traffic east and west wherever you want. So if we go back here and just apply this real quick, so we'll do an apply F, allow egress traffic. That has now been applied in the namespace. And if we go back to do an exec on Team A in the org1 namespace, let's try this out. So now can I curl google.com? Now I can. So I'm still under the scrutiny of that deny all, but I have opened up the ability to egress. And here's another interesting thought. So based on this, am I able to go to Team B org2? And I'm not. So when you think about this, why would you be blocked? Well, you're technically able to egress out to Team B, but is Team B allowing ingress traffic in from Team A? It doesn't seem like it, right? So let's go back and see if we can solve this as kind of a final example here. So we could actually go to our org policy YAML file, just kind of use that as our original template here. And so let's change this up a little bit. So this will apply to org2. We'll call it Team NetPol. I guess that won't hurt anything. So we've got the match selector on Team B. And we want to allow ingress traffic on port 80, which should look pretty good. This time we don't want to do any egress stuff. We're just going to let Team B still be completely locked down from an egress standpoint. So we'll get rid of all of that. All right, so we're allowing all ingress traffic inside of here. And maybe we even want to get more specific. So let's grab some of these rules here. So we will say from, I'll get rid of this. All right, so we're going to say from the namespace selector org1. All right, and we're going to say only for Team A. So this is a very restrictive policy. Only Team A will be able to access us inside of port 80 based on this policy. So now that we've got this set up, let's go ahead and apply it here. So we'll do an apply, and we will do the org.pol.yaml. It has now been created. And let's see if it now works for us. So if we exec back into Team A, and we curl to Team B, so Team B, org2, now we're able to access Team B. So you can see kind of the beauty of this, having this global network policy enforcing cluster-wide things, and then starting to be able to poke holes with these namespace-scoped network policies. And again, the network policy I chose to use here was just the Kubernetes network policy. Now, this oftentimes leads into kind of the final question I want to address, which is, what should I use? Should I go completely all in with my CNI plugins network policy CRD if they offer that? Should I use the Kubernetes one? And it just kind of depends. It depends a lot on your use case, and it